Okay, everyone, let's begin. So this is the first paper that we're doing today, November 22, paper 4.1. We will be doing difficult questions from these papers, 4.1, 4.2, and possibly 4.3 as well, depending on how much time we are left with. So there are not many questions from this first paper, 4.1. What I'll do is some of them that have slightly more words, I'll have a look at them and see if any of them looks very difficult, and we could just do that question. And mostly you have questions from the other papers then. This is straightforward, forces in equilibrium. This is momentum, loss of kinetic energy. No one has asked about this. Question 4 is acceleration. Yes, okay, it's also not that complicated. M1 workshop, how long will it last? Most likely around 2.5 hours, 2.5 to 3 hours between that, 2.5 to 3 hours, inshallah. Okay, distance traveled by the block during the 4th second. For this, you could use limits if you want. Use find the displacement function. Use limits from t equals 3 to t equals 4, or find the displacement at this point. Find the displacement at this point. Find their difference, and you will get that. So hopefully you can do that. Question 5 is about kinematics, and then they're asking about total distance traveled here in this interval. Okay. Question 6 is about limit and equilibrium, and then this. Okay. All right, let's have a look at these two questions from this paper. This is November 2022, paper 4, variant 1. We're starting with first question number 5 for this. Question number 5 for this. We'll do 5 and 6 from this paper, and then from the next one, we'll do 6, 7, and 8. And then from the next one, 3 and 7, inshallah. Okay, so that's what we will be doing. For this part, Mazum, as I said, you will find the displacement at time equals 3, find the displacement at time equals 4, find their difference, and that will give you the distance traveled for this part. Okay, it will be on Saturday. Yes, the M1 workshop, that's going to be on Saturday, 3rd of May. Saturday, 3rd of May. Around 5 p.m. to 7:45 p.m. That's the tentative time. M1 syllabus is not that much, so hopefully it's not going to be like P1 that took a lot of time. This should not take as much time. Okay, let's have a look at this now. Question number 5 from this paper. It says the particle P moves on the x-axis from the origin with an initial velocity of minus 20 meters per second. The acceleration at time t seconds after leaving O is given by this. A equals 12 minus 2t. Sketch a velocity time graph for 0 to 12, indicating the times when P is at rest. That's a 5-mark question. They've given you some blank space here down here, in which you have to draw that graph. And then they've given some line space here as well. They've given some line space here as well, where you can do any working that's required. Okay. P3 and S1, I'm not sure if I've posted that in the group yet or not. P3 is going to be from 16th to 17th, both 2 days basically, 16th and 17th May. That will be for P3. And for S1, we will be doing that on 10th of May, inshallah. Okay. So the S1 workshop is going to be on 10th of May. P3 on 16th and 17th, and M1 on 3rd May, inshallah. All right. Okay. Let's have a look at this. So they've given some line space here to basically do any calculations that are needed. Yes, I'll be posting that in the group. So I already posted that in the WhatsApp group already about the workshop. but I will be, of course, telling you before we start as well. Okay, now we know it's moving at some speed. Its initial velocity is -20. That's what we're given. Acceleration is a. Acceleration a after leaving the point O, that's given by 12 minus 2t. We want to sketch a velocity time graph from 0 to 12. Now, how do you do that? We would first have to find the velocity function for this, right? How do you find the velocity function? How do you go from acceleration to velocity? You integrate it. 12t minus 2t squared over 2, that becomes t squared. But remember, whenever we integrate and we're not inputting any limits, we always have to use a plus c there. So we have a plus c here as well. And now, how do you find the value for c? We know that the initial velocity was what? -20. Initial velocity means velocity at time equals 0. So when time is equal to 0, we know that the velocity is equal to -20. That's what we're given. So we can use that now to find the value for the c. Let's input t equal to 0 and v equal to -20. What do we get from that? -20 equals 0 minus 0 plus c. The value for c turns out to be -20. So the velocity function therefore is, the velocity function is 12t minus t squared minus 20. That's the velocity function. Now that we've got the velocity function, we want to sketch the velocity time graph. It's going to be a quadratic graph, right? It's a quadratic graph. It's minus t squared plus 12t minus 20. It's a quadratic function, N-shaped graph like this. They're saying indicate the times when p is at rest. At rest means when velocity is equal to 0. So you would have to put velocity equal to 0 and find the times at which velocity equals 0. Let's do that. 0 equals minus t squared plus 12t minus 10 equal to 0, or minus 20 equal to 0. Can we solve this quadratic equation? If I take all terms to left side, that becomes this. Now, can we factorize this? We can use 10 and 2. So t squared minus 10t minus 2t plus 20 equal to 0. That gives us two factors, t minus 10 and t minus 2. T either equals 10 or t equals 2. These are the two values of t that we're getting. These are the points at which the particle is at rest. So what is the velocity time graph going to look like now? You can draw that here. This is velocity, this is time. We have found the two x-intercepts, right? The points where the velocity becomes equal to 0. So now we can get an idea about the shape of the graph from that as well. Time is going from 0 to 12. So let's mark 0 here, let's mark 12 here. What are those important points at which the velocity is becoming 0? Time equals 2 and time equals 10. Let's mark those points as well. We can say this is 2 here, and then this is 10 here. The graph has to pass through the x-axis, the horizontal axis of these points. What else do we know? Initial velocity was -20. That's one thing that we know. And that's it. We can draw that graph. We can sketch the graph like this. We can say right in the middle, since it's a quadratic function, right? Quadratic functions are symmetric. So it's going to be a symmetric curve. So its maximum point is going to be right in the middle when time is equal to 6, right? Between the two x-intercepts, because of the symmetry of the graph, that's where the maximum point is going to be. So the graph is going to look something like this. We'll say this goes like this here. And similarly, on the right side, it goes like this. Again, because of the symmetry of the graph, we know that at time equals 12 as well, the velocity is going to become -20 at that point as well. So if I were to mark this point here first, this is going to be -20, the initial velocity. At time equals 12 as well, the velocity is going to be -20. So it's going to look like this. That's what the graph looks like. That's what you had to draw in the first part. This is your velocity time graph. Now, they have not asked you to show the value for the maximum velocity here. So you do not necessarily need to show that. It's not necessary. You can leave that, and that's okay. Okay, you don't have to show the maximum velocity. Okay. That's what the graph is going to look like. We'd have some value of velocity here. It doesn't matter. We don't have to specify that. Is this all right? Any problems with this? Okay. All right, good. Let's look at the next part now. It says find the total distance traveled by P in the interval from 0 to 12. Now, when we're looking for distance traveled, we have to break the journey at the points where the velocity becomes 0 because that's where the direction is changing. Now, in this case, we can see the direction is changing at the point 2 and the direction is again changing at the point 10, right? Now, to simplify our working, however, so one idea could be that we find the displacement function from this. What's the displacement function going to be? V is equal to, the velocity function is minus t squared plus 12t minus 20. That's the velocity function. We find the displacement function from this minus t cube over 3 plus 12t squared over 2. That will be 6t squared minus 20 times t. And then you input limits in this. You break your journey into 3 parts because the velocity is changing at time equals 2 and the velocity is again changing at time equals, velocity is becoming 0 at time equals 2 and the velocity is again becoming 0 at time equals 12. So you could break the journey into 3 parts like this. You could say, let's evaluate the displacement from 0 to 2 separately, and then 2 to 10 separately, and then 10 to 12 separately. And then add them up together. That's one idea. But you could make it slightly more efficient. Because of the symmetry of the graph, we could say whatever is the distance traveled up to the point 6, we can just multiply that by 2, and that will be the total distance traveled, right? We could also do it like this. Find the distance traveled in the first 6 seconds, and then just multiply that by 2. That will reduce some of that working. We'll not have to do it for 3 parts separately because we know for the first part and the last part is going to be the same. So that's another idea that we just find these 2 parts from 0 to 2 and 2 to 6, right? That will be half the journey, and then just multiply that distance traveled by 2. Okay, that will be slightly more efficient. Let's do that. Let's input the limits. Input 2 in this one, minus 2 cube divided by 3 plus 6 into 3 squared, 2 squared minus 20 into 2. Subtract from this the case when you input t equal to 0. In this case, all of them become 0 and you get the result. What do we get from this? What's this first result? Does anyone have this? Minus 56 over 3. Yeah, so it's going in the negative direction at that point. So that's minus 56 over 3. That's this part. And then from 2 to 6, that's the second part. We could say that's going to be limits 2 to 6. Input 6 in that, minus 6 cubed divided by 3 plus 6 into 6 squared minus 20 into 6. Subtract from this the case when you input time equals 2. We've already found that value, that is minus 56 over 3. So we can just input that here directly, and that will give us another result. What's this going to be? 128 over 3. So that's the distance traveled in the first half of the journey, and the other half is exactly symmetrical to this. You can see that in the diagram. Find this distance traveled. Find this distance traveled first of all, making the values positive. 56 over 3 plus 128 over 3. Whatever this value turns out to be, you multiply that whole number by 2, and that will give you the total distance traveled. You can see what that turns out to be. What's this? 368 divided by 3, and that's your final answer. Thank you. That's the total distance traveled. Okay, that's what we were looking for. That's part B. Let's move on. Question number 6. That's the next one that you're asking about. Figure 6.1 shows particles A and B of masses 4 kilogram and 3 kilogram respectively. It's a question that we've done before as well as a very similar questions to this. 4 kilograms, 3 kilograms, we've got their masses given and shown in the diagram as well. Angle is 30 degrees. String is taut. Okay, so all of this information is shown in the diagram. There's nothing new that they've mentioned here. The plane is rough and the particles are in limiting equilibrium. Find the coefficient of friction between B and the plane. Okay, how do you find that? You represent all the forces acting on A and B. A has weight acting in the downward direction, that's 40 Newton. There's tension acting upwards. At B, we've got tension acting in this direction. There's reaction acting perpendicular to the surface, that's this. There's going to be weight that acts vertically downwards, that's 30 Newton. And what about friction? Where is friction going to act? This weight is more, right? Even though they've not mentioned which side the particles are going to move in, but you can clearly see that this is 40 Newton and the component of B in this direction, that's going to be less than that, of course, because its total weight is 30. So that component is going to be even less than that. So the particles are going to try and move this way, that A goes downwards and B goes up. Now, if that happens, what about friction? Where does friction act? Friction opposes the motion of B and that acts in this direction. These are all the forces that are acting. Resolve the weight for B. What are the two components going to be? One in this direction, another in this direction. If this angle is 30 degrees, we know that this angle is also going to be 30 degrees. So the component in this direction is 30 cos 30, and the other component is going to be 30 sine 30. Okay, and now for the particle B, these forces are going to be equal. Forces that are acting in the perpendicular direction to the surface, R is going to be equal to 30 cos 30. What do we get from this? 30 under root 3 over 2. And that's 15 under root 3. That's the value for R that we've got. Okay. R equals this. And now we can use Newton's second law of motion in both of these objects one by one. A is moving in the A is about to move in the downward direction. Sorry, it's limiting equilibrium. It's not moving. So we just equate the opposite forces for both of those objects. We don't have to use Newton's second law of motion because it's not moving. Just equate the opposite forces for A. We just have T equal to 40 Newton. For the object B, we already have done this calculation for B. Perpendicular forces are equal to each other, and the forces along the surface, what are they going to be? T equals F plus 30 cos 30, 30 sine 30. That's another equation that you get. T equals F plus 30 sine 30. Now, since its limiting equilibrium friction is going to be at its maximum value, we know the value for T. T is 40. F is equal to mu R. Mu is what we have to find out. Mu into R, that is 15 under root 3. Plus 30 sine 30. Sine 30 is 0.5, so it becomes 15. And that's if we can find the value of mu from this. You can see what that is. That's 6 marks. Extremely straightforward. What do we get? What's the final answer from this? The value for mu? 0.962. That's the final answer that we get. This is 0.962. That's coefficient of friction. Okay. That's part A. Let's move on. Part B, it says it's given instead. How is this for 6 marks? Yes, I have no idea, because maybe they've compensated in the next part. Next part here, this is a bit difficult, although it's also not going to take that much time. But yeah, it's fairly straightforward. It's given instead that the plane is smooth. Okay, so now there is no friction and the particles are released from rest. When the difference in the height, in the vertical height of the particles is 1 meter. So this distance is 1 meter. Now, use an energy method. When they say energy method, what does that mean? That means work done by the driving force that is going to be equal to change in kinetic energy plus the change in potential energy plus the work done against resistance. Right, that's what we have to use. Now, is there any driving force here? No, there's no driving force. If you consider the overall system, that's what I'm saying. If you consider the overall system, in the overall system, there's no external force that's acting apart from weight. It's only weight that's making them move in the overall system. So if we apply this work energy principle on both the objects together, for A, we've got tension acting here. For B, we've got tension acting here. But when we consider the overall system, tension is part of that system. So we don't consider that. That basically just cancels out each other's effect. So we don't consider that. For the whole system, what else? Change in kinetic energy, do we know that? We have to find the speed of the particles at the instant when the particles are at the same horizontal level. Okay, so what's happening is A is going to move downwards and B is going to move up the plane. And at some point, they are going to be at the same horizontal level like this. Okay. Now, let's suppose A moves X units downwards, B would move X units along the surface. We know the total distance between the vertical heights, that's 1. So the tricky part in such questions is finding the value for X. How much is A going downwards? How much is B going up along the surface? How do you find that? You can do that using this right angle triangle. You can say, let's make a right angle triangle like this. In this right angle triangle, we know that the angle here is 30 degrees. This angle is 30 degrees. And if this complete distance is 1 and this is X, then this right angle triangle that we've got, its perpendicular side is going to be 1 minus X, right? Because the total is 1. Total up to this point is 1. And the upper part is X. So the lower part is going to be 1 minus X. So we've got this right angle triangle. We can use this right angle triangle to find the value for X. What is that going to be? Perpendicular over the hypotenuse. That's 1 minus X divided by X. That should equal sine of 30. And that's 0.5. So 1 minus X equals 0.5X. X equals 1 over 1.5 or 2 over 3. Right? That's the value of X that we get. Once we've got that value of X, we can just apply this principle now. Change in kinetic energy, what would that be? Since the particles are connected to each other, their speeds are going to be the same. So we can consider them together if we want. What's the total mass for them? Or let's just do them separately in case you get confused by that. 1 over 2 into mass of A. What's that? That's going to be 4. So 4 into final speed, that's V, initial speed 0. Plus the change in kinetic energy for B, that's 1 over 2 into 3 into V squared minus 0 squared. It also started from rest and its final speed is V. Both of them are going to have the same speed when they reach the same height, because the string is taut, the particles are connected to each other. Whatever speed one particle moves at, the other particle should also move at the same speed, right? We could also consider it together by using 7 as the mass, right? 7 is the mass of the whole system. That will make it a bit more efficient. What about the change in potential energy now? Change in potential energy for A. Let's think about that. Mass is 4 into 10 into change in height. How much is height changing? X is 2 over 3 and it's decreasing by 2 over 3. So this is 2 over 3 and A is going downwards. If A is going downwards, its height is decreasing. The change in height is negative. So we say this is minus 2 over 3. Okay. Plus. On the left side, we've got 0. Mass of B, that is 3 into 10 into change in height for B. B is going up. What's the change in its vertical height? It's 1 minus X. What's the value for this? 1 minus 2 over 3. That is 1 over 3. That's the change in height for B. That's going up by 1 over 3. Plus work done against resistance, there's no resistance because they're saying that the plane is smooth. You could also use the conservation of energy principle here. That would also work. You could also do that. In this case, because there's no driving force, there's no resistance. But this also works. What do we get? We get from this, we can find the value of V now. It becomes 7/2 V squared. Evaluate this, whatever the strengths are to be, minus 80/3 plus 10. That's minus 50/3. Find the value of V from this, see what that turns out to be. What's the value for V? 2.18. That's our final answer. Again, not that difficult. The difficult part is figuring out the change in height. I think that's the tricky part. That's what requires some thinking. But we've done multiple questions like this already now. So it should be something that you should be able to figure out relatively easily. Okay. No problems. Can I move on? Okay, so that's from this paper. From this paper, we only had 2 questions that we wanted to do. Let's look at the next paper now. So the next paper is November 2022, paper 4.2. Now we'll have a look at difficult questions from this paper. Let me have a look at the poll now and see which questions you've asked about from this paper now. November 22, paper 4, variant 2. This is the next one that we're doing. Okay. So from this paper, it's primarily question 6 and then maybe 7. I'll have a look at that if that's difficult. But mainly 6. 6 is what a lot of you are asking about. Let's look at that. So this is November 22, paper 4.2. Let's go to question number 6 from this paper directly. Look at this one. Three particles A, B, and C of masses 0.3 kilograms, 0.4 kilograms, and m kilogram respectively, they lie at rest in a straight line on a smooth horizontal plane. Okay, so we've got these three particles, they lie at rest on a smooth horizontal plane. The distance between B and C is 2.1 meter. A is projected directly towards B with speed 2 meters per second. That's the speed of A. After A collides with B, the speed of A is reduced to 0.6, still moving in the same direction. Show that the speed of B after the collision is 1.05. Okay, so how do we think about this? It's simple conservation of momentum in the first part. The collision is between A and B, right? So let's say this is A and let's say this is B. Now, what are the speeds before and what are the speeds after? Let's say this is before and this is after. A is projected towards B. Initially, they were at rest, right? So A is projected towards B. It goes towards B at a speed of 2 meters per second. And B is at rest at 0 meter per second. Okay. What happens afterwards? What happens afterwards? After, just give me a second. I'll be back. Okay, so A is moving towards right at 2 meters per second. B is at rest. What happens after collision? They're saying after collision, speed of A is reduced to 0.6 meters per second. And we have to find the speed of B. Let's call that BB. Let's use conservation of momentum. Momentum before collision equals momentum after collision. And that will give you the value for BB. Let's see what that turns out to be. Momentum before collision, consider right side positive. Momentum before collision is mass of A. Mass of A is 0.3 into velocity of A, that's 2, plus 0 for B. Momentum after, that's 0.3 into 0.6 plus VB times 0.4. And that will give you the value for VB. You can see what that turns out to be. 0.6 minus 0.18, which is 0.42 divided by 0.4. What do we get? 1.05. We get that from this. 1.05, that's the value that we were looking for in the first part. Now it says after this collision between A and B, B moves directly towards C. Okay. Particle B now collides with C. After this collision, the two particles coalesce and have a combined speed of 0.5 meters per second. Find the value for n. Okay, now how do we think about this? We've got this particle A here, and we had this particle B, and we had this particle C. After the first collision, now B is moving. This is before the second collision. Now B is moving to the right at 0.5 meters per second. C was at rest. C was at rest. The two particles coalesce after this and they move at a combined speed of 0.5. So let's call that combined particle BC. And this is moving at 0.5 meters per second. What are the masses? Mass for B was 0.4 kilograms. Mass for C was m kilograms. So for BC, it would be 0.4 plus m kilograms. These are the masses. Again, let's apply conservation of momentum. Momentum before collision, that should equal momentum after collision. Momentum before collision, mass of B, that is 0.4 into velocity, that's 0.5. Was that 0.5? That was 1.05. Why did I write 0.5? 1.05. So that's 0.4 into 1.05 plus velocity of C, that was 0. So momentum is also 0. After collision, that becomes 0.4 plus m, that's the mass, times the velocity, that's 0.5. This velocity is 0.5. Multiply this by 0.5, and that will give us the value for m. You can see what that turns out to be. On the right side, we have 0.2 plus 0.5 m. On the left side, this is going to be something. And we get the value of m from that, which you are saying turns out to be 0.44. So m equals 0.44 kilograms. That's this part. Okay, now the first two parts were fairly straightforward. We start to apply conservation momentum on each of them separately, and we get the result from that. Let's move on. Now it says, find the time that it takes from the instant B and C collide until A collides with the combined particle. Okay. From the instant when B and C collide until A collides with the combined particle. Now we have to consider what happens from the beginning now to understand at what position A is. Do we have any distances given? Distance between B and C is 2.1 meter. Okay, so that's the distance that we're given, 2.1 meters. So after A and B collide, so when A and B are here, both of them, from this point onward, let's consider what's happening. This distance is 2.1 meter. Okay. B was going to the right side at what speed? 1.05 meters per second. And A, after the first collision, it was going to the right at 0.6 meters per second after the first collision. So A is also moving to the right and B is also moving to the right. A is moving at 0.6 meters per second. And C was at rest at this point for now. Okay, so this was the initial situation from which we have to find the time. Okay, so from the instant when B and C collide until A collides with the combined particle. Now, B goes towards C and it collides with C. How much time does that take? We need that because we also need to figure out how much has A moved to the right in that time, right? Because otherwise we would not know the position for A at that instant when the collision between B and C happens. So we first need to figure out how much time does it take for B to reach that point. Can we find that? It's a smooth surface. There's no friction. It's moving at constant velocity, constant speed. So we can say the time taken by B to reach C from this point onward. What's that going to be? Distance is 2.1 divided by the speed. That's 1.05. That turns out to be 2 seconds. So it takes 2 seconds. Now, in these 2 seconds, A would have also moved some distance to the right. What would that distance be? 1.2 meters. Distance moved by A in these 2 seconds. That will be speed into time. That's 0.6 into 2, and that will give us 1.2 meters. So when B and C collide, here and they've coalesced to become one single particle, where has A reached at that point? A has reached at this point such that the distance from its starting point is 1.2 meters. How do I represent that? I can say this distance in green, this is 1.2 meters. So A will be here at that point. And now what's the remaining distance between these two particles? The remaining distance between these two particles, that is 2.1 minus 1.2. What's that? That's 0.9 meters. So 0.9 meters is what is still left. Now, after B and C collide, that combined particle, at what speed is that moving? The combined particle is moving at 0.5 meters per second to the right. So now the combined particle is moving to the right at 0.5 meters per second. And A is moving to the right at what speed? It's still moving at 0.6 meters per second. These are the speeds at which both of these particles are moving. A is moving at 0.6 meters per second to the right, and B is moving at 0.5 meters per second to the right. Now, how much time does it take for A to catch up with BC and collide? Now, every single second, you see what's happening? A is moving to the right a distance of 0.6 meters, and B is moving to the right a distance of 0.5 meters. How much are they getting closer to each other in that time? In 1 second, they're getting closer by 0.1 meter, right? 0.6 minus 0.5. We call this concept the relative speed, right? What's the relative speed of these particles? What's the relative speed going to be? Relative speed means the speed at which the distance between the particles is reducing. Every second, A moves 0.6 to the left, to the right, sorry. The combined particle moves 0.5 meters to the right every second. the distance between them reduces by 0.1 meter per second. Every second, the distance reduces by 0.1. Think about this. If you have this point A and you have this point B, and this particle A and particle B, they have an initial distance of 1 meter with each other. Now, A moves a distance of 0.6 meters to the right in 1 second. B moves a distance of 0.5 meters to the right in 1 second. Where are the particles going to be? This is the point 0.6. If this was 0, this was 1, and this is 1.5. So what's the distance between the particles now? It was initially 1 meter. Now it's 0.6 to 1.5. That's 0.9 meters. How much has the distance reduced? It has reduced by 0.1 meter. So that's the relative speed between the particles, the speed at which the distance between them is reducing. Okay. So that's what we figured out. That's relative speed, 0.1 meter per second. And now, how much time do they take to catch up with each other? The distance between them is 0.9 meters. So what's the time taken then for this distance to be covered? Every second, only 0.1 meter is covered. So the time taken is going to be distance over the speed. Distance is 0.9 divided by the speed, that's 0.1, and that gives us 9 seconds. And that's our final answer. That's what we were looking for. Is that okay? It's fairly tricky, but you're getting these questions a lot in the recent papers. Multiple times we've seen in the recent papers, in 2024 papers as well. I think there was one in 2023 papers as well. So it is coming up again and again. So you need to understand this concept of relative speed well. Any issues with this? Make sense? Okay, good. So that was question number 6 from this paper. That was the one that you guys were asking about. Question number 7. After this, that's not that difficult, I think. Okay, what I'll do is I'll do it quickly. So I'll just give you hints quickly so that we can move on to the next paper after this as well. We have two questions to do from the next paper. Yes, 2 questions from the next paper as well. So there's this particle P. It starts from rest at a point O. The acceleration is given by this. Now it's starting from rest. That means at time 0, the velocity is 0. Find the velocity of P at time equals 4 at this point. How do you do that? We can find the velocity function A equals 0.3 t raised to power 1 over 2. Find the velocity function from this. We have to integrate this. 0.3 t raised to power 3 over 2 divided by 3 over 2. Whenever we integrate, we have a plus c there. So that gives us 2 into 0.3, that's 0.6, 0.6 over 3. That should be 0.2, I think, right? 0.2 into t raised to power 3 over 2 plus c. That's the value. That's the function for v. What's the value of c going to be? When we know that when time is 0, v is equal to 0. So we can say let's input t equal to 0. That gives us v equal to 0, and that gives us c equal to 0 as well. For that reason, the velocity function becomes 0.2 into t raised to power 3 over 2. Input that value of t in this now, and that will give you the corresponding value for v. See what that turns out to be. V equals 0.2 into 4 raised to power 3 over 2. What's the result that we get from this? 1.6. That's the final answer. Okay. All right, thank you. Now it says it's given that there's no change in the velocity of p at time equals 4 and that the velocity of p at time equals 16 is this. Show that k is equal to 2.6 and find an expression in terms of t for the velocity for time between 4 and capital T. So we have to find the velocity function for this part of the journey, for the second part of the journey. But before that, we need to find the value for k. How do you find the value for k? They're saying there's no change in velocity at t equals 4. That means whatever velocity you get from the first function, that's this, at time equals 4. At time equals 4, you should get the same velocity from the other function as well. Okay? Now, a is equal to 0.3 t raised to power 1 over 2. That's one function. and the time, the value for t is between 0 and 4. In fact, we found the velocity, found the velocity function already. Let's just use that. V equals 0.2 t raised to power 3 over 2. This was valid for time between 0 and 4. What's the second acceleration function? The second acceleration function is a equals minus k into t raised to power minus 3 over 2. Can we find the velocity function from this? Let's integrate this as well. Minus k remains as it is, t raised to power minus 3 over 2 plus 1, that becomes minus 1 over 2, divided by the new power, that's minus 1 over 2 plus c. And now it becomes, you take this to the numerator, 2 gets multiplied there, minus they get eliminated, and you have 2k t raised to power minus 1 over 2 plus c. How do you find the value of c and k now? You've got this point here saying when time is equal to 4, the velocity is the same that we found in the first part. Let's input that point. We can say let's input t equals 4 and the value for v as 1.6. That's 1 point that we know. Let's input that here. Let's see what we get from that. 1.6, that equals 2k into 4 raised to power minus 1 over 2 plus c. Let's simplify this to get 1.6 equals 2 over 2. That will become this k plus c. That's one equation. Then we have another point given. The other point is when time is equal to 16, the velocity is equal to 0.3. Let's input that point now. That's another piece of information that we have. 0.3 equals 2 into k into 16 raised to power minus 1 over 2 plus c. Let's simplify this to get 0.3 equals 2 over 4, which is 1 over 2, that's 0.5, 0.5 k plus c. That's another equation that we have. Solve these two equations simultaneously, you get the values of k and c. What do we get from this? What are the values of k and c that we get? Okay, Abdul Rafi, I'm sorry, I just saw your message. I'll go back to that after this question. Please remind me before we move on to the next paper. Remind me about this question again. K is 2.6 and C is equal to minus 1. Thank you. So K turns out to be 2.6 and C equals minus 1. They wanted us to write down an expression for velocity for the second part of the journey. What's that? That is now going to be V equal to 2 into 2.6 into t raised to power minus 1 over 2 plus c, the value for c is minus 1. Simplify that and that gives you v equals 5.2 into t raised to power minus 1 over 2 minus 1. That's the final result that we get from this. Okay, so that's the velocity function for the second part of the journey. That's what we were looking for. Let's move on. Let's move on to the next part now. It says, given that t comes to instantaneous rest at t equals t, find the exact value of t. Now we've got the velocity function. The velocity function is this. That's 5.2 t raised to power minus 1 over 2 minus 1. If it comes to rest, you put v equal to 0 in this. Find the value of t at that point. 0 equals 5.2 into t raised to power minus 1 over 2 minus 1. Take 1 to the other side, 1 equals 5.2 divided by t raised to power 1 over 2. We can make the power of t positive. If you take that to the denominator, now this gets multiplied there. So you have t raised to power 1 over 2 equals 5.2. Square both sides, and that will give you the value for t. You can see what that is. 5.2 squared. What's this value? $27.04. 27.04. That's what we were looking for. Is that okay? So they were asking for capital T. We can say capital T therefore equals 27.04. Now they're saying find the total distance traveled between time equals 0 and time equals t. That means time equals 0 and time equals 27.04. How do we do that? We have to check for any change in direction. They've already made us do that. When v is equal to 0, we're getting only one value of time for the second part of the journey, and that's 27.04. That means in the second part of the journey from time equals 4 to capital T, there's no change in direction. For the first part of the journey, have we checked for velocity equal to 0 anywhere? For the first part of the journey, we have not, but we can check that. If we put v equal to 0 here, we only get t equal to 0. So there's no change in direction, right? So you can check that there's no change in direction by inputting v equal to 0 in both of them. Whenever you have distance traveled, you always have to check for that. So there's no change in direction. All you have to do then is you've got one velocity function that is valid for time between 0 and 4. What's that velocity function? Zero 0.2 into t raised to power 3 over 2. And you've got another velocity function that is valid for time from 4 to 27.04. And that function is v equals 5.2 into t raised to power minus 1 over 2 minus 1. That's the other function. Integrate both of them, input limits, and you get the result from that. S equals 0.2 into t raised to power 5 over 2 divided by 5 over 2. Input limits from 0 to 4 in this. And the second one, S equals 5.2 t raised to power 1 over 2 divided by 1 over 2 minus t. Input limits from 4 to 27.04 in this. And get the result from this. You can do that now. You have to make sure that you show those steps in which you're inputting the limits. Input 4, then input 0, input 27.04 in the second one, and then input 4. Find their difference. You have to show this working, that working is necessary. If you write down the answer directly, that is not going to be acceptable. Okay, so you have to show this working. That's necessary. When you're inputting the limits and then write down the final answer. From that, you get one value from here, you get another value from here, add those two numbers, and you get the final answer. Okay, all right, you can do that. Can we move on? Okay, so that was this paper. This was a fairly straightforward one. Question number 6, part C, that was difficult. But again, if you've done enough practice, you have seen other questions like this in other papers as well. So it's kind of similar to that, using the concept of relative speed. Let's move on now to the last paper that we're going to take today. But I just need a few minutes break, 2-3 minutes, and then we start with this paper. We will be doing 2 questions from this paper. 2 questions from this paper. Question number 3 and 7. Questions 3 and 7. These are the 2 questions that we will be doing from this paper. Okay, November 22, paper 4, waiting 3. Questions 3 and 7. Okay, but I'll just need 2-3 minutes break and then we resume after that, okay? Okay, let's resume with this. November 2022, paper 4, gradient 3. Let's have a look at some questions from this paper now. So from this paper, you're asking about questions 3 and 7. Yes, 3 and 7. Okay, I missed 3 there. Okay, so a ring of mass 4 kilograms is threaded on a smooth circular rigid wire with center C. The wire is fixed in a vertical plane and the ring is kept at rest by a light string connected to it, the highest point of the circle. The string makes an angle of 25 degrees to the vertical. Find the tension in the string and the magnitude of the normal reaction of the wire on the ring. Okay, so this is the ring that we've got. What are the forces acting on the ring? Let's represent them first. Since we have equilibrium, right? It's at rest, that means it's equilibrium. Opposite forces are going to be equal to each other. So let's represent the forces are acting at the ring right now. We've got the weight of the ring that acts vertically downwards. That will be 40 Newton. What else? There will be tension. This is a string, right? So there's going to be tension that acts in this direction away from the ring and towards that point to which it is connected. And what else? Weight we have represented, tension we have represented. There is no friction as such because it's a smooth wire. Reaction, where is the normal reaction going to be? Now, reaction is supposed to be perpendicular to the surface, right? Reaction is perpendicular to the surface. Now, what's the surface? Surface is circular. What is perpendicular to a circle? Normal to the circle, right? So normal to the circle means at this point, if we were to join this ring with the center, join this point with the center, this is going to be perpendicular to the circle at this point, right? Because tangent is perpendicular to radius and normal is perpendicular to the tangent. So normal, when you extend that always passes through the center of the circle. So this is going to be the direction of reaction. Now it could be in this direction, it could be in this direction, one of these two, right? That depends on the other forces that are acting, but it's going to be one of these two directions, right? That it's going to be perpendicular to the circle at that point. Now, which one of these is it? Can we figure that out somehow? Let's think about it. If this is 40 Newton, what are the components of weight going to be, of tension going to be? Tension has this component. That's one component for tension. This is another component for tension. If this angle is 25 degrees and this angle here is also 25 degrees, the component acting adjacent to the angle, that's T cos 25, and the component acting on the other side of the angle, that's t sine 25. Now, think about it. Tension has one component acting upwards and one component acting in this direction, right? And one component acting in this direction, another component acting in this direction. Now, the component that's acting upwards, weight is acting opposite to that. So, weight will be countering that. But the force that's acting to the right side, what force is countering that to keep it in equilibrium? There will be normal reaction. In which direction does that act now? There were two possible directions, as we said. It could either act towards the center of the circle, but in that case, its components are going to be in this direction and this direction. There will be nothing on the left side, so that's not what it's going to be then. The direction of normal is going to be this. This is the normal reaction. This is the direction which the normal acts. What are the components going to be? One component to the left side here and another component in the downward direction. These are the two components of normal reaction. Now, what about the angle? If this angle is 25, if this is 25, then this is also 25, right? Because it's an isosceles triangle. This triangle, it's an isosceles triangle. So this angle is also 25. Now that's 25. What about this remaining angle now? That was 50, this total. So the lower angle is 40 degrees. This is vertically opposite angle. This angle is also going to be 40 degrees. So what are the components of R going to be now? R cos 40 and R sine 40 here. These are the components of the normal reaction. Okay. All we have to do now is equate the opposite forces, and that's going to give us the result. You'll see what we get from that. T cos 25, that should equal R sine 40 and plus 40, and T sine 25, that should equal R cos 40. And that should give us the values of T and R. Let's solve these two simultaneously, and let's see what we get from that. Force is acting towards the left side. There's only one force, that's R cos 40. That should equal force acting towards the right. That's T sine 25. Force is acting in the upwards direction. That's T cos 25. That should equal R sine 40 plus 40. You get these two equations, solve them simultaneously, you get the value of T and R from this. So what I can do is I can say, let's make R the subject from the first equation, maybe. It becomes T sine of 25 divided by cos of 40. Input that in the other equation. So that gives us T cos 25 equals R, which is T sine 25 over cos 40 times sine 40 plus 40. And that will give you the value for T. You can see what that turns out to be. What's the value of T that we get from this? It will be something like this, right? 40 divided by, the calculator needs to be in degrees mode, cos 25 minus sine 25 divided by cos 40 into sine 40. 72.5, yeah. So that's what you get, 72.5046, 72.50. That's the tension. Input that in the other equation now. You get the value of R from this. 72.5 into sine of 25 divided by cos of 40. What does that turn out to be? 40 Newton. Okay. And that's it. That's the final answer. That was 6 marks. Figuring out that normal reaction and the angle, that was the tricky part. Once you have figured that out, the rest is straightforward. You just make two equations, solve them simultaneously, and you get the result from that. Is that okay? Okay, can I move on to the next question? Okay, good. This was question number 3. Now the last question for today, question number 7. Question number 7 from this paper. Let's do that. This one. Now this is again one of those questions involving kinematics, momentum. Now that's going to take too long, I think, just by looking at it. It's a pretty long one. It's 12 marks. Let's get started. So it says particles of masses 1.5 kilogram and 3 kilogram, they lie on a plane which is inclined at an angle of alpha to the horizontal. Okay. Tan alpha equals 3/4. Now it's very important that you have a look at, skim through the paper in the beginning so that you identify any questions like this, so that you remember that you need to hurry up in the earlier questions and leave enough time for this. You need at least 18 to 20 minutes for this in the exam. At least that much time, at least 20 minutes. It's 3, 6, and that's 12 marks. 12 marks, 20 minutes. You will need that time for this question. So you need to, do the earlier questions relatively quicker then. Particles of mass is 1.5 kilograms and 3 kilograms. We've got them there in the diagram. Tan alpha equals 3/4. AB part is smooth and B to C part is rough. 1.5 kg particle is held at rest at A, and the 3 kg particle is in limiting equilibrium at B. The distance AB is x meters and BC is 4 meters. That's given in the diagram as well. Show that the coefficient of friction between the particle at B and the plane is 0.75. Okay, so we're talking about B right now. What are the forces acting at B? We have the weight of B, that's 30 Newton. We've got normal reaction that acts in this direction. We consider normal reaction as well because B to C part is rough. So we will have to consider friction. For friction, we also represent normal reaction. What other forces do we have? We have friction. If it's trying to move down the plane, friction is opposing that acts in this direction. And now what are the components of 30 Newton going to be? If this angle is alpha, we know that this angle here is also going to be alpha. So this component is 30 cos alpha, and the other one is 30 sine alpha. Now, let's just equate the opposite forces. It's limiting equilibrium. That's what they're saying. So R should equal 30 cos alpha and F should equal 30 sine alpha. What do we get from this? R equals 30 cos alpha. We are given the value for tan alpha. Just put this on your calculator. Tan alpha equals 3/4. Find tan inverse and then, find sine of alpha, cos of alpha from that. Since it's perpendicular over base, I think this is going to turn out to be perpendicular, which is 3. So that's sine alpha will turn out to be 3/5. Put this on your calculator, you'll get this. And cos alpha is going to turn out to be 4/5 from this, right? Because tan was perpendicular over the base. Hypotenuse is 5 from this. So we get this 3/5 and 4/5. So R is 30 cos alpha. That will simplify to 30 into 4/5. That's 24. R is equal to 24. Equate the other forces. F equals 30 sine alpha. Sine alpha is 3/5. 30 into 3/5. What does that turn out to be? That's 18. Friction is 18. F equals mu r. You can find the coefficient of friction from that. Because it's limiting equilibrium, friction is supposed to equal mu r. We get 18 equal to mu into 24. The value of mu turns out to be 0.75. And that's our final answer. Okay, that was part A. Now, the next part says the 1.5 kg particle is released from rest. The 1.5 kg particle is released from rest. Okay. That's this particle. A to B part is smooth. That is released from rest. In the subsequent motion, the two particles collide and coalesce. The time taken for the combined particle to travel from B to C is 2 seconds. The coefficient of friction between the combined particle and the plane is still 0.75. Find the value for X. Okay, now how do we think about this? A is released from rest. A is released, 1.5 kg particle is released from rest. And it moves from A to B. And then at B, it collides with that 3 kg particle. And then that combined particle goes further from B to C, and we have the coefficient of friction for that particle. So there are multiple parts of this journey. First of all, let's understand what happens as a 1.5 kg particle moves from A to B. Okay, that's the first part that we're considering right now. Let me write that here. 1.5 kg particle as it goes from A to B. What do we know about this part of the journey? It's going downwards, so we consider this direction positive. We know that it started from rest. U is equal to 0. What else do we know? We know the displacement to be x meters. Displacement is x. What else? We know acceleration. Do we know acceleration for this part of the journey from A to B? Do we know what acceleration is going to be? A to B part is smooth. A to B part is smooth, right? On a smooth surface, when weight is the only force that is acting, remember what acceleration used to be? 10 sine theta, right? On a smooth inclined surface, when weight is the only force acting, we know that acceleration is going to be 10 sine theta. Right? So we can write that value directly. A is 10 sine theta. So we know the acceleration for this part. Acceleration is going to be 10 sine of theta. Sine theta is, in this case, the angle is alpha. Sine alpha is 3/5. N into 3/5, that gives us 6. That's the value for acceleration. Okay, so we know initial velocity, we know that displacement is x. We know acceleration is 6. We do not know the final velocity. We do not know the time taken. Okay, so that's what we know about A to B part of the journey. We have to find the value for x eventually. What we can do is, since now at the point B, this particle is going to collide with the 3 kg particle, we need the velocity of this particle, right? What's the velocity of this particle going to be? The final velocity at the point B. What's that? Can we find that in terms of x somehow? Let's do that. Let's find that velocity in terms of x. V is what we're trying to find out. What equation connects these things? V, U, A, and S. V squared equals U squared plus 2AS. I'm finding this because I need to use conservation of momentum when they collide with each other. So I need the speed at which it hits the other particle. V squared equals 0 squared plus 2 into 6 times displacement, which is x. And that turns out to be V squared equals 12 times x, and V equals square root of 12 times x. Now this is the velocity of 1.5 kg particle. Velocity of 1.5 kg particle at the point B. This is what we wanted to find out there. This is the velocity of the 1.5 kg particle at the point B. Okay, now this is square root of 12x. What about the next part of the journey now? Next, we have to consider, this is 6 marks and this is the space that they've given us. Okay. Let's keep it on this side. Now, at this point, what happens is the two particles collide and they coalesce. Let's apply conservation of momentum now for that collision that's happening. Conservation of momentum. Momentum before collision, moment equals momentum after collision. Now, what do we know about their collision? A 1.5 kg particle, that's one, and the other particle is at rest, that's 3 kg particle. Okay. Momentum before collision, that should equal momentum after collision. So now we're talking about the second part of the journey, when they collide with each other. What's the momentum before collision? We're considering the downward direction positive. Momentum for the 1.5 kg particle, that's going to be 1.5 into the velocity. Velocity is this, square root of 12x. Plus momentum of the other particle, that's a 0, because that was at rest. That equals the combined particle, its mass is going to be 4.5, right? Times the velocity of that combined particle. Let's call that combined particle something. Let's call that combined particle P. So Vp. Okay, so Vp, what does that turn out to be? 1.5 into square root of 12. Can I just simplify that on my calculator? 1.5 into square root of 12, that's 3 under root 3. So we have 3 under root 3 times x. No, x is inside the square root as well. Divided by 4.5. And that's 2 under root 3 over 3. This is 2 under root 3x. Both of them inside the square root divided by 3. Now, what's this giving us? This is the velocity of the combined particle, velocity of the combined particle just after collision in terms of x. Make sense? This is velocity of P. So we're calling the combined particle P after collision. Okay, now what happens after this? So this was the second part. This is what we did first, and then we did this. Now, the combined particle starts moving downwards. It goes from B to C now. It goes from the point B to the point C. That's 4-meter distance. So now we're considering the combined particle. Let's call that particle P. And now that combined particle is going from the point B to point C. Now, what do we don't know about this part of the journey? We know the initial velocity of this combined particle. We found that here in terms of x. So we can say the initial velocity is 2 under root 3 times x divided by 3. What about acceleration? We'll have to find that. Let's leave that for now. Displacement is 4. We are considering downward direction positive. So we can say displacement is 4. What are we looking for? Eventually, we want to find the value for x. Okay. It takes 2 seconds to go from B to C. So we know the time taken, that's 2 seconds. And we can find the acceleration now. How do you do that? Using Newton's second law of motion now, because they have given us the coefficient of friction. They've given us the coefficient of friction. What I'll do is I'll just take it down there. Let's find the acceleration. First of all, what would that be? We'll have to think about the forces that are acting. We already thought about them before. What are the forces that are acting? R is equal to 30 cos alpha. That's still true. The value for R is 24. That's going to remain the same as before. There's nothing that's changing there. Coefficient of friction is still the same as before. That's 0.75. Find the acceleration. Forward force minus the backward force. That should equal mass into acceleration. Right? There's only one forward force, 30 sine alpha. Backward force is F. So we can say resultant force equals mass into acceleration. Forward force is 30 sine alpha minus the friction. That should equal mass of the combined particle. That's 4.5 times acceleration. Sine alpha, what was the value for that? Sine alpha was 0.6. So 30 into 0.6 minus the friction. Friction is mu times r. Mu is 0.75 times the value for r. That was 24. That's the same as before. That equals 4.5 times A. And you get the value of A from this. What's the value of A that we get? Won't force change because they coalesce? Which force will change? Oh, yes. You're right about that. I did not consider that. Reaction will change actually. Reaction will not be the same. Reaction is not going to be the same because their mass has changed now, right? Their mass has changed. Since their mass has changed, these forces are going to be different. We have to consider that again. Sorry about that. That's not going to be what it is. We have to make that diagram again. I was trying to save some work, but that made us do some errors. Let's represent that here again. Now we've got the combined particle. It has greater mass. Yeah, it has greater mass now. So that's going to be 4.5 kilograms. So weight is now 40 Newton, 45 Newton, sorry. So according to that, everything else, changes as well. The angle here was alpha. So this angle would be alpha. This will be 45 cos alpha. The other one will be 45 sine alpha. Will have friction here and will have reaction here. So reaction is actually going to be 45 cos alpha now. Reaction is going to be 45 cos alpha. So R equals 45 cos of alpha. What's cos alpha? Cos alpha was 0.8. 45 into 0.8, that's going to be 36. R equals 36 from here. And when the value of R is 36, let's use Newton's second law of motion now. We get 45 sine alpha minus the friction. That equals mass, which is 4.5 times the acceleration. Sine alpha, that was 0.6. 45 into 0.6 minus the friction. Friction is mu times r. Mu is 0.75 times r. The value of r now is going to be 36. That equals 4.5 times A. And that should give you the value for acceleration. You can see what that value turns out to be. What's the value of A that we get? What's the value for A that we get? 0. Seriously, after all this, we got 0. Okay, so acceleration is 0. What that means is it's moving at constant speed. Then if it's moving at constant speed, we could use a constant acceleration formula as well. That will still work. So this is A equal to 0. Or you could just use speed equals distance over time as well. That will also work in this case. S, U, A, and T. Which equation connects these? We can say S equals UT plus half AT squared. Let's input values in this. A is 0, right? So it just becomes 4 equals 2 under root 3 times x divided by 3 times t, which is 2 plus 0. And that will give you the value for x. You can see what that turns out to be. You would not try to do so much clutter here. You have 2 additional pages normally in the exam. This is an additional page. You'll do some working here. If you still need more space, you have a blank space here. You can work here as well. Make it easier for the examiner to understand what you're doing. So don't make so much clutter here like I've done. Do it on the additional page. Okay. I did not do that because I would have to scroll up again and again so much. That's why I'm just doing it here. But when you're doing it physically, you can just, turn the page and that's okay. What does this turn out to be? 4 and 4, they get cancelled. When 4 and 4 get cancelled, we are left with 3 equals under root 3x. Square both sides, that gives you 3x equals 9 and x equals 3. Is that the value of x that we get? X equals 3, right? And that's our final answer. Yes, so all of that work to get an acceleration of 0. But then the value of x turns out to be 3, and that's what we were looking for. That's our final answer. Is that okay? Any problems with this? That was fairly tricky. A lot of work for these 6 marks. Okay, let's move on now. It says find the total loss of energy of the particles from the time just give me a second. Okay, find the total loss of energy of the particles from the time the 1.5 kg particle is released until the combined particle reaches C. Total loss of energy of the particles. Okay, so we've got 2 particles here. Initially, they have some kinetic and potential energy. What are they going to be? We know the value of x is 3 now, so we can make a right angle triangle that looks something like this. To find those heights. Okay, so let's call this HA, let's call this HB. Can we find the heights now? We can say HA over the hypotenuse, which is 3 plus 4, that's 7. HA over 7, that should equal sine of alpha. That will give you the value for HA, height of the point A. Sine alpha is 0.6, so 7 into 0.6, that will give you some value for HA. What does that turn out to be? Height of the point A. We need that for potential energy, right? What do we get from this? 4.2. Okay. Now both the particles are reaching the ground eventually, right? What about HB? HB over the hypotenuse, that's 4 for the smaller triangle. For this triangle, hypotenuse is 4, height is HB. This equals sine alpha again. So that's HB equal to 4 into 0.6. That will be 2.4. 2.4, that's HB. So we have the heights that they're losing, and they were both at rest initially. Yeah, so they were both at rest initially, so that's the total energy initially. Initial energy, what's that? That is equal to mgh for the first particle, mass of the 1.5 kg particle, into 10 into its height, that's 4.2, plus mass of the other particle into 10 into its height, that's 2.4. That will give you the initial energy. There was no kinetic energy initially. At the end, there's no potential energy if we consider that the ground. We can find the final kinetic energy from this. What's the initial potential energy that we're getting? What's this value? 135. At the end, the combined particle that was moving at what speed? Do we know that? Did we have the final velocity here? No. Okay, so you have to find that now. You have to find the final velocity when it reaches the ground. Since acceleration is zero, in fact, since acceleration is zero, that means the speed is not changing. So whatever it was before, that's the same. So you can say the final velocity would be 2 under root 3 times x is 3, divided by 3. And that will give you some value. That's 2. Right? That's the velocity at the bottom. Half into mv squared. Combined particle has a mass of 4.5 into the speed. That's 2 squared. And that will give us 9 joules. That's it. That's the final kinetic energy. There's no potential energy at the end. So what's the loss of energy then? Just find their difference and see what that gives you. Loss of energy. That turns out to be 135 minus 9, and that's 126 joules. That is the final result that we get from this. Okay, so that last part was really straightforward. The second part, that was quite tricky. And that's it. That's what we wanted to do here. Any quick questions before we end? Okay, yeah, thank you for reminding me about that. If A catches up 0.1 meter, okay, that was the previous paper, this paper. Yeah. So you were saying if A catches up 0.1 meter per second, wouldn't it reach in 5 seconds? Why? The distance between the particles was 0.9 meters. So if it's catching up by 0.1 meter every second, so to catch up by 0.9 meters, that will take 9 seconds. Every second it's catching up by 0.1 meter. Their initial distance from each other was 0.9. BC is also moving. That's what that's where 0.1 is coming from, right? So initially they are 0.9 meters apart from each other. In 1 second, A moves to the right 0.6 meters. B moves to the right 0.5 meters. How much does A travel more as compared to B? It travels 0.1 meter more. So that means A gets closer to BC by a distance of 0.1 meter in 1 second. What's the total distance between them? That's 0.9 meter. How much time would it take? 0.9 over 0.1. That's 9 seconds. Both of them are moving. That's why we're saying the relative speed for them is 0.6 minus this 0.5. That's 0.1. Okay. All right. Anything else? Anything else before we end? It had a threshold of 30. Oh, that's understandable then. This was November 22. Threshold of 30. That's still quite low, let's say. The first question is easy. The second is also not that hard. Some people would have found this difficult because of the direction of reaction. So this would have lost people marks, maybe 3 marks here. Let's say they get half of this right. Okay, this is also actually another not very straightforward question. You can use limits here, and they will work. During the second motion, during the second, that means from time equals 1 to time equals 2, they are traveling this much. And then during the 4-second means from time equals 3 to time equals 4, they're traveling this much. So you make two equations from that. You can use limits if you want, and then solve that to find that initial speed. This is actually quite tricky as well. So because of this, probably the threshold might have been a bit low. This is not that difficult. Okay, this is not that difficult. Yeah, makes sense. 30 is understandable for this. So on Friday now, we'll be doing that paper that had the lowest threshold of all M1s that we have seen until now. And that is October-November 2021, paper 4, some variant of paper 4 from that session, paper 4-2, I think. We'll do that on Friday, inshallah. And then on Monday, we do difficult questions from June 2022 papers, inshallah. All three papers, we'll do difficult questions from those three papers on Monday. And then on Tuesday, it will be an open-ended session where you can ask any questions that you have. And we have a revision workshop. On the Saturday, do not forget that we will be having that from around 5 p.m. onward, inshallah, this Saturday, 3rd May. All right, that's it. I'll see you again in the next class. Allah Hafiz.